All right, today we are going to go over plotting points in the complex number plane, sort of a combination between complex numbers that you guys may remember from lots of things you've done in the past, and then also polar coordinates. So a complex number normally is written in the form a plus bi, but instead of doing a plus bi like we normally would, we're going to do that same number, but it's going to be in this form instead. It's going to be z equals x plus yi, like that. And that number can be interpreted geometrically, which means we can graph it on an xy axis. Each point would correspond to a certain complex number, and every complex number would correspond to a point. So we call this the complex plane. The x-axis is the real axis, the a or x-axis, and the y-axis would therefore be the imaginary axis. So if you wanted to graph a particular point, so for example, if you were to graph, let's say 3 plus 4i, we'll do a right there, then you would basically label the 3 as the x, the 4 is the y. So you would basically do x plus yi. So you'd go 3 to the right, and you would go 4 up, and that point right there would be labeled as a. Or I'm sorry, in this case, we would label it as z1. So z is typically the name of a point that is based on a complex number on the complex plane. So a couple others here. Z2, 5 to the left and 1 up. So that would be negative 5, 1. So right there we have what would be called the point Z2. C, let's see here, Z3, so 6. So what that would be is the same thing as saying 0 for y. So you do 6 plus 0i. So you just be graphing the point 6, 0, and we'll call that Z3. And just a couple others here. Z4, that would be 2 to the left and 7 up. That would put you right about there. Z4. And then finally, the last one we'll do is right there. Z5. That would be 4 to the left and 5 down. So 4 to the left, 5 down. And we'll call that one Z5. So every point can be graphed if it's got a complex form, which we do x plus yi. Now, any point on the complex number plane has what's called a magnitude or a modulus, and the notation for that modulus looks like this. Okay, it's got the z, looks like an absolute value, but that's actually called the magnitude or the modulus, and the definition of that is the distance, how far it is from the origin to that point. Okay, so in order to figure that out, just like we've done many, many, many times, Pythagorean theorem is involved there. So if you go x to the right and you go y up, right triangle there, then you know that x squared and z squared together, x squared plus, x squared and y squared together, that equals a lot of different things, but that would definitely be the distance from, that would be the square, of the modulus like this. If you squared the modulus or the magnitude, you would get that. So if you took the square root of both sides, the square root of x squared plus y squared is the magnitude, which is also the length from the origin directly to that point. So the definition is consistent for everything we've talked about in the past. This is kind of like the absolute value of a complex number. Just like we have the absolute value of a real number, if you actually did the absolute value of 7, you get 7, negative 7, you would also get 7 absolute values. That's what they do. So sometimes we will call this an absolute value, but it can also, but we're probably going to call it mostly the magnitude or the modulus. So if you have a complex number, its conjugate, which we're going to denote as z with a bar on top of it, okay, that's the conjugate of z, conjugate. And if you multiply a number and its conjugate together, okay, you would end up with this. So let me show you why this works out the way that it works out. So if z is x plus I, yi, and if its conjugate is x minus yi, and you do what we would call like FOIL or any other method you would use, you would end up with x squared and then minus y squared I squared. And of course, I squared is just -1. So therefore, you would just end up with x squared plus y squared. And that's kind of what we always do with conjugates, a plus bi, a minus bi. So if you wanted to, you could kind of take what we just did and combine a couple different things. The square root of x squared plus y squared. This is x squared plus y squared. And these two can be connected because they would equal that. Okay, so let me just kind of run down the general process here of what I just did. Okay, so the absolute value or the modulus is going to equal this. Okay, that's always true. And then if this is z, x plus yi, and this is the conjugate of z, x minus yi. So, and if you took these two and you multiplied them together, you would get x squared plus y squared. So what we get is then the next step, I'm going to write it down like this. Z times the conjugate of z, okay? If you multiply those together, you would get this. And you'll notice these two are the same. You just have to take the square root of that. So it kind of follows then, just like this theorem right here says, that if you take the magnitude of an absolute value or the magnitude of a complex number, then that would be the same thing as the square root of the complex number times its conjugate, like that. Okay, so now moving on, the next thing that we are going to do, let me go ahead and save this screen now. That's everything we need to do there. Take a picture. All right, so the next thing that we are going to do is take a look at a complex number and talk about how we can convert between rectangular and polar form. Just like with anything that we've done recently, you have a complex, you have a polar and a rectangular form. Both of those two things can be expressed. So as we already have done, the connection between x, r, and theta is cosine. X equals r cosine theta and y equals r sine theta. Well, that's going to be true for x plus yi as well. So here's the definition of how we write x plus yi, or z, in polar form, assuming that theta is only between 0 and 2 pi, and r is greater than 0. So if z is a complex number, x plus yi, then it's going to be x, which is r cosine theta, plus y, which is r sine theta, and then of course you have I there. And then if you wanted to, you could factor the r out, so it would end up being r cosine theta plus I sine theta. So when you look at that, you really should just think r x plus y, iy. Okay, that's basically what that says right there. So if you wanted to look at the graph then, you basically end up with the same thing that we've talked about before, except for this is now r. That's the hypotenuse of the triangle, and that would be theta, which is the angle that it makes around the polar graph. So the angle theta is sometimes called the argument of z if it is written like that. So it turns out that the r, is the same as what we called the magnitude or the modulus just a minute ago. So it's x squared plus y squared, and you take the square root just like that. Okay, so let's go ahead and practice just a few examples of how you can convert between a complex number in rectangular x plus yi form and then polar form. All right, so let's go ahead. We'll start with 4 minus 4i. Oh, and one other thing also, once in a while, you will see it written like this as kind of a shorthand. If it's r cosine theta, r cosine theta plus I sine theta. Some textbooks or other teachers in the future may abbreviate it or do something like this. They would say r cis theta. And that's just kind of like a shorthand for cosine plus I sine is just cis. There's really nothing technical about that or anything. All right, so let's graph and look at how we would convert 4 minus 4i first of all. All right, so first, I think it would make sense probably to go ahead and graph that. So that would mean x is 4. So we'll go ahead and go 4 to the right, and then we'll go 4 down. So that would be the point z in this particular situation, okay? So you'll notice we went 4 to the right, we went 4 down, and that would be 4 minus 4i. So if you were going to do this in a polar way, you think about the polar axis here, and then you would rotate all the way around the circle until you finally were pointing in that direction. So we're looking for theta there, and we're looking for the length of r, which would be right there. So to go through the process here, let's go ahead and we'll do this one over on this side. So the first step is to think about if we want r, okay, we already have x and we already have y. But if we want r, we're going to use this connection right here. R is, because that's how you would get a polar form, okay? Remember, polar form is r theta. R radius circle, theta is the angle rotating around the circle. That's what I mean by polar form. So r is x squared plus y squared under a square root. So in this particular example, r would be the square root of 4 squared plus 4 squared. So 16 plus 16, which is 32. And if we simplify that to its most simple form, we would end up with this, the square root of 16 times 2, which is going to be 4 square root of 2. So that's the value of r. And if we figure that out on our calculator, I think we would get approximately 5.66. Okay, so that's r. We also therefore need theta. Now, in order to get theta, we can go ahead and use, I think we could probably use, well, actually sine or cosine. We're going to use both of them just to make sure. So we want to make sure that we end up in quadrant 4 to the right and down. So an angle in quadrant 4, what we're going to do is the sine and cosine. So we'll use this rule first, r sine theta. That's going to give us y. So therefore, what is r? R is 4 radical 2. And then we'll do times the sine of theta. And that's going to have to equal our y value, which we already know that our y value is -4. Okay, so we'll continue on that process right there. So therefore, the sine of theta is going to equal -4 divided by 4 square root of 2. And if we simplify that out, we should end up with 1 over the square root of 2. It will be negative, but we'll go ahead and simplify it to something that we know. So that right there, that should be the sine of theta. And our goal is to figure out what theta is, and we'll do that here in just a second. And then we'll do cosine also, because if the sine is negative radical 2 over 2, we could be in either quadrant 3 or 4, but we want to be in quadrant 4. So we're going to use the cosine. Our cosine theta is equal to x. Okay, so therefore, we will do r, which is 4 times the square root of 2 times the cosine of theta. And that, of course, is going to have to equal what is x in this case, 4. So it looks very similar. We end up with the cosine of theta equals 4 over 4 radical 2. And if we simplify that, we would get square root of 2 over 2. So that's the cosine of theta. So the only way you can have that sine and that cosine is if theta would have to be a pi over 4. So we can do this a couple of different ways. I think we'll go ahead and use 7 pi over 4. So theta will be 7 pi over 4, and that's because of the two angles that we had right there. If you wanted to, you could also call theta negative pi over 4. It's the same thing, and if you look at the graph that we drew, it would land you in the same place, okay? So finally, after all of that, if we wanted the polar form of z, okay, the polar form would be r is 4 radical 2, and theta is 7 pi over 4. So that would be perfectly correct. We could also do it as 4 radical 2 and negative pi over 4. Either way should work out the same. So that's how we would do that, okay? I'll go ahead, let me give you the results for the next two, and then if you want, we can work through those. Actually, you know what? I think I could probably find some room on the right side of the screen. So that would be for that first example right there. Okay, let me see if I can mark off some space here. Okay, so let's look at the second one right here. 3 radical 3 plus 3i. So if you think about what 3 radical 3 is, 3 radical 3 to the right and then 3 up. So let's go ahead before we graph that and do some conversions up here like that. All right, so x is 3 radical 3 and y is 3. So step one, if we want to find the polar coordinate r theta, is finding r. So r is going to be the square root of x squared, that's x, plus y squared, that's y. So r is equal to, let's see, that would be 9 times 3, so that's 27. That would be 9. So we would end up with the square root of 36. So that would be 6. R is 6 for the polar coordinate for that second graph down there. Okay, now we're going to do sine and cosine. So we can write down that the, let's see here, r sine of theta, so this is r, times the sine and cosine. So we'll do r sine of theta. That's going to equal y. The y value is 3. So we're looking for an angle in quadrant 1 that has a sine of 3/6, which is 1/2. So we're going to figure out when that's true, and then we'll do the same thing for cosine. R times the cosine of theta is equal to the x value, which is 3 square root of 3. Therefore, the cosine of theta is going to be the square root of 3, let's see, 3 square root of 3 over 6, which is going to be the square root of 3 over 2. So the only angle that could possibly have that and be in quadrant 1, like it says z would be the angle that has a measure of, let's see here. I'm going to go ahead and just draw myself just a quick little picture. Make sure I get this right. So the sine is 1/2. The cosine is square root of 3 over 2. So that angle should be pi over 6. It's like 30 degrees. Okay, so the polar form for that second one, and then we'll draw the graph as well, is going to be r6. Theta is pi over 6. So we got 6 and pi over 6 for that one. Okay, and then let's go ahead and we'll draw a picture of the graph here just so we make sure we get this right. So we'll use let's use the x plus yi form. So 3 square root of 3, I'll do that real quick. So that's going to be about 5.2. So I'm going to go about 5.2 to the right about there. And then I'll go 3 up. We'll put us about right there. All right, so that would be the point Z. And we know that that would be correct because it looks like everything should work out perfectly as far as that goes. Okay, that looks like about a 30-degree angle from the polar axis. Everything else seems to work out perfectly fine. Okay, so then the last one we'll do will be over here, -4 plus 3i. All right, so finally this one, -4 plus 3i. X is -4, y is 3. So now I'm going to go ahead and just do the same thing I did before to get r square root of x squared plus y squared. So that's going to be the square root of 25. So that makes r 5. And then I'm going to write down r times the sine of theta is equal to the y value, which is 3. So I'm looking for a sine of theta is 3/5. And I'm going to need my calculator to figure that one out. I'll get that in just a second. And then r cosine of theta, that's going to equal the x value of -4. So I'm going to write down the cosine of theta is -4/5. So let me go ahead and make sure I got a good picture of this graph. So that's going to be 4 to the left, 3 up, puts me in quadrant 2. 4 to the left, 3 up to get that particular point there. So now I'm going to just need to figure out the angle measure based on looks like a 3, -4. That would therefore be a 5 on the triangle. So theta will be the angle from the polar axis around to there. And r is already known to be 5. So that's r. All right, so let me write down the polar form now. Okay, r is 5. Now, to get theta, I am going to need to go ahead and use my calculator. And we'll go ahead and get this in radians, and we can just round to a couple different decimal places as we go. So I'm going to do, let's see here. If I do the inverse sine of 3/5, and if I do the inverse cosine of -4/5, I should be able to locate the angle in the second quadrant. Second, let me make sure I'm in the correct mode. Let's go to radians. All right, quit. So I'll do second sine of 3/5. Okay, and that's 0.6, which is actually going to be not even quite at pi over 2. And then I'll do the inverse cosine of -4/5. And that should get me more closer to where I want to go. Yep. Okay, so those two angles, and here, this may make more sense if I do this in degrees, just so you can see it both ways. So if I do the inverse sine of 3/5, I get about 36 degrees. If I do the inverse cosine of -4/5, I get about 143. So the 143 is also 2.49, or let's call that 2.5 radians. So I'm going to use that one. That's going to be the one that will make the most sense. Okay, so that's 2.5 in radians. That's about 143 or so degrees. And this would be 0.64 in radians. And that's about 36.9 degrees. Okay, so the angle that I want in radians will be that one right there, because that's the one that's located in quadrant 2. So I'm going to go ahead and write, let's see, 2, what was the radian measure for that one? Sorry, you guys can't see my screen here. I'm writing and I'm not even seeing that here. All right, I'm going to go ahead and get rid of this one. Okay, there we go. So the polar form would have to be 5 and 2.5. That's in radians. Okay, or you could also do 5 and approximately, these are approximate angles, 143 degrees. Either one of those two would work out well. Okay, so that's how you would graph a single complex number based on rectangular form and then going to polar form. All right, so we're going to convert from a complex number or something, a point in the complex plane that is in polar form, and we're going to try to convert that to rectangular form. So the difference between polar, and the reason I know this is polar is because it's got an angle measure. The reason I know it's complex is because it's got an I. Rectangular form is going to be this, x plus yi. That's going to be what we mean by rectangular form. So to make that conversion, it's a pretty simple process. So right now we have an r value. So 4 is r. So here I'm just going to write down a generic form of this. R times the cosine of an angle plus I times the sine of that same angle. So to convert that, I'm going to do the following process. I'm going to actually locate on a circle with a right triangle. We always draw a picture. We've done this many, many, many times. I'm going to locate where 120 degrees would be, right about there. And I'm going to figure out what is the cosine and sine. So the cosine is -1/2. The sine would be the square root of 3 over 2. So I'm going to use that information to rewrite this as 4 times the cosine, which is -1/2, plus the sine, which is square root of 3 over 2. And there's an I connected to that as well. And then I can basically just distribute that. So it would end up becoming -2, 4 times -1/2, plus, and then we do 4 over 2, which is 2. So that would just be 2. And there's an I there as well, along with the radical 3. So that would be the best version of a rectangular form. So there's x and there's yi, if you wanted to graph it that way. So that's basically the process that we would follow with that. So let me go ahead, I'll do a couple more of these so you can see the general idea. So for this one, we're going to do 5 times the cosine of pi over 6. And if you think about pi over 6 on a unit circle, if you were to draw a picture of that, pi over 6 would have a cosine that would be the square root of 3 over 2. Again, stop and draw a picture if you need to. And then plus I, and then the sine of pi over 6 is going to be 1/2. So then we would simply write, 5 radical 3 over 2, and then plus 1/2 I. Or I guess, 5 over 2i. So here I'll write it like this. 5 over 2i, and that would be just fine for a rectangular form. So we know it's rectangular form because there is no angle measure. That means it's not polar, but it is still complex. It does still have an I. All right, and then finally this last one, we are going to need to use our calculators because it's pi over 15, and pi over 15 is not really an angle measure. I would expect you to have exact values like I would for the previous 2 examples. So I'm just going to go ahead and write 3.5. I'm going to use my calculator. I'm going to make sure that I'm in the right mode, radian mode. And I'm going to do the cosine of pi over 15 and just round to 3 decimals, 0.978, 0.978, okay, plus, and then I times the sine of pi over 15 as well, second pi divided by 15. So when I do that, I get 0.208, 0.208, like that. And then if I distribute that, again, this is an approximation, and that's completely fine. I'm going to do 3.5 times the 0.978, and I'm also going to do 3.5 times the 0.208, 0.208, like that. All right, so I end up with 3.423 plus 0.728i. And that would be the rectangular form for that particular complex number based on the polar form. All right, the next thing we're going to do is do some operations with polar numbers that are in, with complex numbers that are in their polar form. So the first thing I'm going to do is go through, there's a couple of rules here that you want to always go back and refer to as needed. So if you have 2 complex numbers, Z1, Z2, you can multiply them or you can divide them. So when we multiply them, we go through the following process. We multiply their R values, and then we take the cosine and sine of the angles that would be associated with each one, but we add those angles up. And then for division, we divide the R values, but we subtract the angle measures when we do their sine and cosine. So let's go ahead and go through the process of multiplying and dividing two complex numbers that are written in a polar form. So if this is z and that's w, let's go ahead and we'll do the multiplication first. And I'm going to use this rule right there. So r is 3 for z and r is 5 for w. So I'm going to multiply those two r values together to get zw, the product. So I'm going to do 3 times 5. That'll become 15 in just a second. And then I'm going to do the cosine of, and I'm going to add the 20 degrees plus the 100 degrees there. And then I'm going to do plus I times the sine of, and I'm going to go ahead and add those angles again. So that would be 20 degrees plus 100 degrees. All right, so the next step is going to look like this. I'm going to have 15. I'm going to have the cosine of 120 degrees. And I can find the cosine of 120, but I don't need to in this problem because the directions clearly state that I'm just going to leave that in polar form, 120 degrees. So there we go. So that would be my best version of a polar form. And again, if it says polar form, means angle measures are still part of the result. If you look up here at the top, we changed from polar to rectangular. Okay, so that's the product of ZW. Let's go ahead and do the quotient of Z and W. So Z divided by W is going to look like this. I'm going to divide them, which means I'm going to divide the R values. So that's 3 divided by 5. I'm going to take the cosine of, I'm going to do 20 degrees minus 100 degrees. It's got to be in that particular order, plus I times the sine of, and I'm going to do 20 degrees minus 100 degrees again. There we go. So my final result, pretty straightforward, is going to look like this. 3/5 up front, cosine of negative 80 degrees, plus I sine of negative 80 degrees, 20 minus 100 being negative 80 degrees. There we go. And then generally speaking, if you can get positive angle measures, which you should always be able to do that, you want to definitely try to do that. So if you think of negative 80 degrees being right about there, actually probably more like about right here. There we go. So we think of that as negative 80 degrees. We want to think of this angle, which would be a positive version, okay, which would be 360 minus 80 degrees. And so I would ask that you use the positive version to get your final result. So that means it would end up becoming Z over W is 3/5 out front, cosine of 280, because that's the same as negative 80, they are coterminal, plus I times the sine of that particular angle. Here, let me make a little more room for myself here real quick, and that should look good. So 3/5 cosine 280 plus I sine of 280. And that would be my best answer for that particular problem, changing from, or keeping it in polar form, but writing it as the quotient of those two complex numbers in polar form.